And what we're going to be doing tomorrow is we're going to be looking at how to find partial derivatives, and we're really just going to get practice at the process. So essentially, if you want to find a partial derivative, don't you consider one variable, one of the letters a variable, and you consider everybody else as a constant, right, as a number, and you treat it such. And it does involve a little bit of weird, you know, the way things might look weird to you. So let's just jump right in. This one I'm picking not because it's difficult, I'm picking it because it's probably quite easy. I want to pick it so that we can just get some of the notation down. This is a multivariable function. Basically, you give me an x and y, I calculate it, and the answer that pops out is a single number. And if you plug that into GeoGebra or something, it tends to look, for whatever word, doesn't it tend to look like the surface of a rolling valley in hills, right? Just bumps go up and down. Occasionally you get some weird, what would be the 3D equivalent of vertical asymptotes. But vertical asymptotes can be a single point shooting upwards or downwards, like a gravity well. And sometimes they can be like someone took a surface and they gave it a tear, and on one side they bent it up, on the other side they bent it down. So it's like a continuous vertical asymptote. So notation-wise, if we write that with the little curly D's, and do not write, I know it's easy to do that, do not write that. That's Calc 1, and that is a pure derivative. This funny little delta is a symbol, it's part of the game, and that is a partial derivative. And so in this case, you differentiate with respect to x. So you basically, that's x squared times a number. So you'll get 2x times a number. In this case here, 2x a number, when you differentiate it with respect to x, you get that. You're comfortable with that? Same question. You will find in some textbooks, they do f with a little baby x to it. That means the same thing as this. You will also find, less common, but I have seen it, that notation. Okay, and that notation. Do you see that essentially there's like 4 different ways of saying the same thing? Now, as far as I recollect, that version is used by the textbook, and it's pretty common. You'll see that a lot, and if you go Google searching and watching videos, that'll be a pretty common notation. And I believe, at least in this textbook, that one there is the other notation that appears from time to time. Now, those who've looked at the homework, would that be fair? Have you seen this version or that version, for instance? No one's seen it? Okay. So, just notation, right? It means find the first partial derivative.
With respect to x?
With
right?
respect to x. Now, if you change the game, I might as well do this now, put it here. If you change the game, but you do a partial derivative with respect to y, this fella gets you 3y squared, but the x squared is still there. And this guy gets you e to the y. And I guess this is an obvious property, at least it is to me, and hopefully to you. There is no reason in the world, is there, that the partial derivative with respect to x should be the same expression as the partial derivative with respect to y. I mean, you're really, you're slicing the shape up in 2 totally different sequences of directions. One, you're slicing it parallel to the x, and the other, you're slicing the shape parallel to the y. You're basically finding the derivative on one of those slices. So that's what partial derivative essentially does. Now, let's think of techniques that you used in Calc 1, and I'll try and pick a partial derivative that has to use it? Well, you could use the power rule. You know, multiply by the power, reduce the power by 1. In fact, wouldn't this question here, at least that piece of it, wouldn't that count? That would be a power rule. You can do a product rule. You could do a quotient rule. You could do a chain rule. And you could also do later on implicit differentiation. And I think I should really call that a method because it's not really a rule. Right, so let's put together some examples of each of those rules being used. Now, if you're going to do a product rule, that's going to be my second example, so I guess that will count as my first. If you're going to do a question that uses the product rule, you have to be aware of when you actually need to use it. Seems a strange question, but here goes. Suppose I do Z equals, oh, I have just found another notation. For first partial derivatives, right? So suppose we had this guy. If you were going to do the product rule, you could have that guy. Or now actually only one of those, if you were finding its partial derivative with respect to x, only one of those actually really needs a product rule. Because for a product rule, don't you need the variable, the expression to have the variable appear twice in a multiplication kind of way? Because if you do this, this looks like a multiplication, which it is, but this is not a product rule. If you want to do a partial derivative of this, isn't the answer just 2xy cubed? Because isn't that really considered a number? So it's like 42x squared. So it's not a product rule. On the other hand, isn't this a product rule? So if you're thinking about product rule in particular, well, you make sure that you know when you should use it and not try and use it in situations where it's not really applicable. That is not a product rule. Neither's that guy. Aren't they power rules? With funny little variable tagged on that looks like a variable, but we're not calling it that, we're calling it a constant. So I might as well use this notation. If I call this A and we'll call this B then. If I was doing A, the partial derivative with respect to x would just be 2xy cubed and a y squared. If I was doing B, which is this guy, then won't I call this fella F and this fella G? And we would do F dash J plus F of G dashed. Plus, wouldn't I still have to differentiate this guy, but in the usual way? Now, in this question then, that guy is 2x. Leave the second one alone. Plus, leave the first one alone and differentiate the second. And then tag on the 2xy squared. And technically speaking, style points still exist, but they are, in many cases, very minor. You know how when you do normal Calc 1, there might be a lot of factoring you could do and a lot of rearranging to make it look pretty, you know, what I call style points. And can you imagine the minute you start jumbling X's and Y's up that most of that doesn't happen? But by sheer coincidence, isn't there a little tidying up we could do here? Not a lot, but I'm going to pull it out anyway. So that would be a product rule, right? So product rules only happen if there's two terms that use the same variable next to each other, multiplication, and you're trying to do a partial derivative of this fella, right, with respect to x. So let me do that same guy and show you that not all things are the same. Suppose I did a partial derivative of this expression with respect to y. Is this a product rule? No. Isn't this just a power rule with a funny constant at the front? So if you differentiate this partial derivative with respect to y, you get 3 times y squared, and this fella, you get 2xy. You see, even the same expression may or may not be using a product rule, depending on which variable you're trying to find the partial derivative of. Now, where is my guy here? This fella here. This one might throw you until you're getting used to it. This would be a product rule if I was doing a partial derivative with respect to x. Great. But I'm going to do a partial derivative with respect to y. What does this get you? Big fat 0, exactly. Which means all I've got is a little 2x squared y. Okay, these are two things multiplied together, but these are two x things multiplied together. And x is considered a constant in this process, and differentiating a number, which is what a constant represents, is always 0, with respect to y at least. Cool. Now, before I go too far, let's show you a little trick. It's a trick of the trade. I'm going to use a property called symmetry. If a function, right, and I'm using z equals or f of x, y equals, if it is symmetric, you can actually save yourself some time by using a symmetry property. What that allows you to do is that if you know one of the two partial derivatives, say this one, you can figure out what the other partial derivative should be. So let's show you a symmetric function. Now, it's not a hard one, but I just want to do one that's easy to start with. This is considered a symmetric function. So what is a symmetric function? If you take your xy and you swap the x for a y and the y for an x, do you end up with the same expression? Well, let's do a test on this. If that x became a y and that y became an x, wouldn't you get that? And isn't that, after a little bit of rearranging, the guy you started with? Now, if you do a partial derivative with respect to x, this guy gets you 6x. Great. I can tell you what the partial derivative with respect to y is. You use this answer, and you can use it to predict the other one. And you say, well, how do you do the prediction? You turn all the x's into y's and all the y's into x's. Now, this is a very simple question, so that's what you get. Right. Got the gist of this? This is called symmetry. So I'm going to try something a bit uglier and show you how you will have to do one of them the hard way, but you can use it to predict the other. Because in a lot of questions, you'll find that they ask you to find not just the first partial derivative with respect to x, but also with respect to y. So let me suppose I've got a function f of xy, and this function is going to be sine x e to the y plus 4x cubed y cubed plus sine of y e to the x. Would you agree that this function is symmetric? If the x's and y's switch places, wouldn't it end up being, with maybe a minor rearrangement, the same guy?
Yes.
So I am going to find both first partial derivatives. Well, if you do df by dx, this guy will get you cosine x e to the y. This guy here will get you 12x squared y cubed, and this guy here will get you sine y e to the x. Now, I guess it's not that hard to do this one, but let's think about how we could use the symmetry property. Don't you just go through each of these terms and switch places, x's and y's? So this fella would become cosine y e to the x. This guy would become 12y squared x cubed, and this guy would be sine x e to the y. Now, can you imagine that you had a really ugly thing up here, and it might be a quotient rule with a chain rule inside it? You know, one of those 10-minute horrible things, right? And you've just found this answer. But the original horrible function had one saving grace. It was symmetric. Couldn't you use this answer to generate the second answer without having to do it all from scratch again? Now, not every function is symmetric, but for the few that are, it's worth it, isn't it? You know, less work to do, saves you some time. Pretty easy thing to remember, right? Switch the x's and y's and call it good. So that was a product rule. Let's do a quotient rule now. Okay. Is this function symmetric? Now, it must be a perfect match. It's not symmetric if it's 3/4 match. So it's not. That kills it. See, if the bottom had said 2x plus 2y, that would have been fine. Suppose it said x squared plus y squared on the top and x minus y on the bottom. Would that be symmetric? Be careful. X minus y, is that symmetric?
No.
No. Think about it. 5 take away 4 is not the same as 4 take away 5, right? That's the easy check. If you're not sure, make the x 5 and make the y 4 and say, look, if I switched the numbers round, would it be the same answer? Well, would you agree that this function is clearly a fraction and there's x's and y's in the top and bottom? So it doesn't really matter which one I go for, x or y. In this case, wouldn't both of them be quotient rules? So I'm only going to do one of them. Let's do the partial derivative with respect to y. Now, I call the top guy f and the bottom guy, we call it g. And it's f dash g take away f of g dashed over g squared. Is that the way most of you would write down the quotient rule? Good, so I'm not really using notation you're unfamiliar with. Now, every stage of the process, especially the bits that involve derivatives, these are partial derivatives with respect to y. So that's going to make a big difference. F dash then, if you take the top line, the numerator, differentiating that with respect to y just gets you 2y. What happened to the x squared?
It's a constant, so it went away.
It went away, it went to 0, right? Now, leave the bottom alone. Take away, leave the top alone. Technically speaking, it's not much of a derivative, but if you differentiate the bottom, don't you just get 1? The partial derivative of the bottom with respect to y is that's 0, and this is just 1. All over 2x plus y squared. So let's do some tidying up. 4xy plus 2y squared. Take away an x squared, take away a y squared. All over that guy. Looks like I'm going to have a y squared left over. I'm going to have a 4xy in the middle. I'm going to have a minus x squared. And on the bottom, I'm going to have 2x plus y squared. And I'm good. I can't see the top factoring. So we're finished. Quotient rule. You can recognize quotient rules pretty easily. Don't they always end up coming from a fraction? Some expression with a top bit, the line that makes a fraction happen, and a bottom bit, right? And when you see that, you're very, very often looking at a quotient rule, at least for one of the two variables. Right. So let's throw in a weird looking one. Oh, let's change the letter of the alphabet. Now, if I decided that I wanted to do the partial derivative with respect to y of this expression, now I could keep it the way it is, but if I did that, is that really a quotient rule? Is y in this expression here a true fraction with y things in the top and y things in the bottom? Not really. I mean, if you split it up, isn't this basically that guy? And in fact, maybe that would be a better approach, because if I write it this way, does it make the derivative easier to see? Because won't that get you 0? And won't this guy get you 2y over x? So I guess the moral of this story is, just because it looks like a fraction doesn't necessarily mean it has to stay as a fraction. And just because it looks like a fraction, or it is a fraction, doesn't mean you're always going to use the quotient rule either. Next question I'm not going to do. I'm just going to show you it as a situation. Right, I'm picking an uglier expression than you're ever going to likely to do. We're not even going to do the question. What I'm using it for is, if you were doing this one, and you wanted to find the partial derivative with respect to x, would you agree this is a really ugly quotient rule? But it's a quotient rule. Would you also agree that that guy is a equally ugly quotient rule? Do you notice anything else about this function? Oh, sorry. Do you now notice anything else about this function? It's
Symmetric.
symmetric. So after I spent 25 minutes getting this guy, won't I spend 30 seconds getting that guy? Can you see that symmetry can certainly help you with some really ugly functions if it has symmetry? Okay, so I'll call that, for the time being anyway, we'll call that quotient rule over with. Is there any questions? I'm assuming that's a good sign, right? Okay, so I'm not sure as when you took this class, you thought you were going to get a quick revision of Calc 1. But essentially, isn't that what we're doing? We're going through all the strategies and all the methods, the major methods used in Calc 1. So we're now going to do a chain rule question. Right, now, don't chain rules get used when the thing is a function of a function? So let's suppose we had z equals the sine of x squared minus 2xy. This is a candidate for the chain rule, isn't it? Now, if you're being asked to find the partial derivative with respect to, say, x, the power rule, the product rule, and the quotient rule basically have formulas, right? F dashes and G's, and the power rule has a formula, multiply by the power and reduce it by 1. The chain rule has a formula, but I don't know if anybody in the universe who actually uses the formula. Isn't the chain rule more a process rather than a formula? Formula to me is somewhere you plug in F dash T, or you plug in G, and you take away, and you do this, and then you square stuff, right? It's a kind of mechanical thing. Whereas the chain rule is a little bit more artistic. This is the sine of a function. So you differentiate it, you get the cosine of the function, and then don't you finish with times the derivative of the function. So I guess that's a formula in the sense I said it in English, but the variation in these is so many of them, isn't it? It's not really an F dash G thing. You can't really write it that way. What is the derivative of this function with respect to x?
2x minus 2y.
Great. Now, there are a few style points. How about pulling out a 2 and doing this? And there's a normal convention in mathematics that when you write down an expression, especially one that consists of various things all multiplied together, that you start with the simplest and you finish with the ugliest. So 2 is typically a number goes first, and then things like x's and x cubed goes last, and things like e to the x plus y or sine of x plus y, some ugly like that goes last. And that's the usual convention for how to write these. That's so that when, can you imagine that there could be really ugly expressions? It kind of makes life a little bit easier if we all write them the same sort of a way, so that you can look at somebody's answer and your answer and you know, match them up pretty quickly. How about this fella? E to the power of the sine of x take away y. And let's suppose I'm going to find the partial derivative with respect to y. You think about it for a few moments. Definitely a chain rule. I would call this a Russian doll chain rule. because it's a thing inside a thing inside a thing, you know, like the little dolls. So let's see how this would work. If you differentiate this, e the sine something, you will get e to the sine of x take away y, followed by the derivative of the sine of x minus y. Well, the derivative of sine x minus y is the cosine of x minus y times the derivative of x minus y. Now, with respect to y, isn't the derivative of x minus y the number -1? Now, if you put them together, you go negative cosine e to the sine x minus y. Do you see my convention of simplest to ugliest? And that would be the way that you would typically write that. In fact, if I asked you to do the partial derivative of this guy with respect to x, this is not symmetric. But I bet you I could have a good guess at the answer. But you agree the only difference is you'd finish with a times 1 instead of a times -1. Chain rule good? Let's try a square root. Square roots are not fun. Let's have h of xy. And let's make it 1 over the square root of x squared plus y squared. Oh, it's symmetric. That's good. And let's suppose I want to find the partial derivative with respect to x. It might look like a quotient rule to you because it's a fraction. I don't think doing this as a quotient rule would be the best way to approach it. What I'm going to do instead is I'm going to look at another way of writing that will lend itself to the chain rule. So would you agree that this is the same thing as 1 over x squared plus y squared to the half power, which is the same thing as x squared plus y squared to the negative a half power? Now, if I write it that way, doesn't it look much more like a chain rule question? Now, if I'd left it in this format, I could have done it as a quotient rule. I guess I'd have to call this guy f, when I have to call this guy g. And wouldn't I still have to call that x squared plus y squared to the power of half? And can you imagine that might actually involve more work rather than less work at the end of the day? And I think most people are in favor of less work. Agreed? If you can do it easier, you should do it. Right, so in this format then, x squared plus y squared to negative a half, well, it's negative a half, x squared plus y squared, and you reduce the power by 1, followed by the derivative of x squared plus y squared is what? 2x. Right, because y squared gets you nothing, right? 2x plus nothing. Now, if I tidy it up a little bit, this guy times this guy, you get negative x. Now we have style points. That's what I call when you take your answer and make it as pretty as possible. That would not be considered the best form for the answer for a question that started life off looking like that. So there are a couple of rules to style points. One of them is factor the heck out of it. So if you can factor things, you should do it, right? Second rule is write it simplest to ugliest, right? We've seen one of those. And then there's a third rule, which is make it look like the original. Now, if the original has square roots in it, I want my answer to have square roots in it, right? So it looks like the original function. So that means I'm going to have to take this negative power and rewrite them as that guy. So at least it's a fraction, right? So that's good. But it's still not got square roots in it, agreed? And so if you want it to really look like the original, you got to figure a way of getting this fella to have square roots in it. So you're going to have to bring back some weird stuff from who God knows when. Math 99, I think. Can't fractional powers be written as radicals? And isn't a half a square root? And isn't 3/2 just a half cubed? So how about the square root of x squared plus y squared cubed? That guy is him. Technically speaking, would not be equivalent. That's the same as that. So you might well have some algebra issues at the end of one of these questions. Oh well. I'm going to use this version because I kind of like it. Remember, this question was symmetric. So I should be able to write this answer down by just using that guy. Agreed? What would the partial derivative with respect to y be, now that you know what x is? Who goes on the top?
Negative y.
Now, technically speaking, would it not become y squared plus x squared? But wouldn't it make more sense to rewrite it as x squared plus y squared, right? So I am switching the x for a y, but after I do that, I realize that y squared plus x squared is the same thing as x squared plus y squared, and there's something, I'm a picture straightener, I don't know how you describe it. Certain things just look right in math to me, and that looks right. Whereas y squared plus x squared, although technically correct, doesn't it kind of just jar a little bit? It just doesn't feel right. So what do I mean by a picture straightener? In our house, if there's a picture that's like off horizontal, I will move it and make it horizontal because it will bug me that it's not horizontal. That's a picture straightener. Now, we all have idiosyncrasies, that's one of mine. It does involve some strange behavior by me. If I go into someone else's house and there's a picture and it's at an angle, I have to fight really hard to not fix it. I have been under strict orders from my wife never to fix anyone's unstraight pictures. But do you know, it's like an itch that you can't scratch. And especially if you're sitting and you're staring at it and there's 4 pictures all perfectly horizontal and then this one's at 30 degrees because the cat knocked it or something. Does nobody feel my pain, or am I the only guy out there that bugs the heck out of?
No, I got you.
Right. I don't know if that's a mathematical brain that we love symmetry and pattern, and things that don't look right kind of annoy our brain, right? So y squared plus x squared annoys my brain. It's like an unstraightened picture, right? An expression that hasn't been fully simplified is like an unstraightened picture, right? It just has a look to it that I can best describe as annoying. So when I look at an expression and it hasn't been, in my opinion, fixed, right, simplified, it bugs me, right? Now, of course, that's the main guys done, but aren't there questions that you end up using a combination of 2 of these? Can you imagine a question that might be a product rule and a chain rule being used together? Or a quotient rule and a chain rule being used together and various other combinations. So let's see if I can do a combination one. So how about Z equals, where shall I go? Let's have an x squared plus y squared cubed times the sine of x times the cosine of y. And I want to find the partial derivative with respect to y. Now, superficially, doesn't this question look like three things multiplied together? And if everything here was x's, it would be three things multiplied together. And we'd have to do an adaptation of the product rule. You know, the one that goes f dash gh plus fg dash h plus fgh dash. I guess we'd have to do that one. But this technically isn't three things multiplied as far as derivatives concerned. Because at any given moment, aren't only two of those three share the same letter. So it's really more like a product rule of two things. So, oops. Let's do the product rule. Well, if you're going to do this guy with respect to y, I suggest that you make this guy your f and you make that whole thing your g. Because isn't that like 5 cosine y's? Right, it's just a constant, right? Okay, it's called sine x, but isn't it just like the sine of 42? It's just a number. So when I do my derivative, it's going to be f dash g plus f of g dashed. If you call f x squared plus y squared cubed, and you want to get f dashed, don't you really want to get the partial derivative, right? Do you recognize that this piece is a little baby chain rule? Isn't it something cubed, where the something's not x, right? It's got more than that, right? So let's see what we get. You're going to get 3 lots of x squared plus y squared times something. Well, times the derivative of x squared plus y squared, which happens to be 2x. So you are going to get 6x x squared plus y squared. So f dashed is 6x x squared plus y squared times g. Oh, let me rewrite it. Question?
Yeah, I was just asking, I thought we were doing it with y.
Fixed question. Easier to fix than to redo, right? We'll do it with respect to x. You quite correct. So, partial derivative with respect to x then. I'm just taking this, I need more room, I can see that right now. It's going to be 6x x squared plus y squared squared times g. G is that whole package here, right? Sine x cosine y. Then you add, leave this guy alone. Now, what do you get when you differentiate this guy with respect to x? Because we've changed the variable to x now. What do you get as this guy's derivative? Sine x cosine y. Partial derivative with respect to x.
When you get
Cosine y.
You will. And cosine x cosine y? Right, x is being considered a variable, right? So if that was sine x on its own, wouldn't the answer be cosine x? And if it was 5 sine x, wouldn't it be 5 cosine x? Well, it's sine x times a constant, so it should be cosine x times a constant. The constant just happens to be called cosine y. Now, still points are coming up now. That is an unstraightened picture. Right? It's like 5 degrees off. There's a little bit you can do to straighten it. Look at the two terms. Is there any common factors that we can suck out?
X squared plus y squared.
And how many of them? A squared or a cube?
Squared.
Squared.
Great. Which leaves me with 6x sine x cosine y plus one of these left over, x squared plus y squared cosine x cosine y. Agreed? Now, I'm going to rewrite one more line and then say, are we finished? Since I don't have enough room, I'm writing this guy at the bottom. Can we straighten this picture a little bit more?
You could pull out a cosine y.
Yeah. And and it's okay to miss things as long as you catch them at the end. Wouldn't it be better if I'd caught it at the start? I would probably have one less line to work right down. Now, that leaves me with 6x sine x plus an x squared cos x plus a y squared cos x. And although these three terms, at any given point, there might be some common factors, there isn't anything that they all three share, so we're finished. Are we happy with first partial derivatives that involve product, quotient, chain, or a combination of those two guys? Now it's like Calc 1. Couldn't we spend the next 2 weeks going through all sorts of permutations? So you're just going to have to look at whatever permutation you get. I don't think the book is particularly bad to you. I'm only saying that superficially. I didn't look at everyone in detail, but the ones I noticed weren't particularly bad. They were pretty straightforward. Power rule, quotient rule, whatever it happened to be. Are we good? Right, so I am now going to do the last guy, implicit. Well, before I do implicit differentiation with partial derivatives, let's just refresh your memory on what implicit differentiation looked like. I don't know, it could have been a year ago. I don't know when you did Calc 1. It could be a fair chunk of time, right? So you might be a bit rusty. So this is Calc 1 world we're talking about right now, right? So although this is going to look like Calc 3 world, it's Calc 1 world. When you take two guys like this and you mix and match them together, in Calc 1, in Math 141, isn't that a two-dimensional function? And it exists, right? As a circle, center, the origin, and radius 2. So if you plotted it in 2D, you'd get that. And the argument goes something like that. If you choose any point on this, won't there be a tangent line? And if there's a tangent line, it has a slope. And isn't the slope of a tangent line essentially what the derivative gets you? So the argument is that this thing has a derivative. So how do we do it? Well, in the Calc 1 world, isn't x always the variable, the independent variable? We don't mix and match them typically. So you differentiate this fella with respect to x, and you get 2x. And then you differentiate this fella with respect to x, and what you get is 2y times something. Because we consider y a function of x, right? And this is Calc 1 world, right? So forget partial derivatives for a minute, right? This is Calc 1 world. So y squared is like f of x being squared, right? It's a function of x. So you end up with an extra dy by dx. Now, what do you get when you differentiate with respect to x? A number like 4. Well, you get a big fat 0. And then after this, don't we spend a little bit of algebra to take this information, and when we're finished, we should be able to say what dy by dx is, right? The derivative. Shouldn't the derivative probably be some combination of x's and y's? That's what you typically would expect. So let's see what happens here. I'm solving it like an equation. I'm going to subtract 2x from both sides. What would I do to both sides to isolate the dy by dx then?
And just divide.
And in this case, it cancels and simplifies. So that is essentially the implicit differentiation process, right, in a nutshell. Now, to do implicit differentiation, we have to take our usual function, and it has to be written with not just z equals x's and y's, which it is typically read, right? But x's, y's, and z's all jumbled up. So for instance, this would be a very simple one to start with. Does anybody recognize what in 3D space all the points that this was true for would look like?
Sphere radius 3.
Right, the surface of a sphere, radius 3, agreed. Right. Now, suppose I was being asked to find the partial derivative of z with respect to x. We are going to employ the strategy that I just used in Calc 1 world and adapt it, right, to the Calc 3 world, right, the partial derivative world. So the rules are typically x is the only variable in town. Agreed? So here goes. Differentiate x squared with respect to x, you get 2x. What do you get if you differentiate y squared, partial derivative, with respect to x? Now don't go Calc 1 on me, go Calc 3. What's the partial derivative? Big fat 0. Do you see there is a change now, right? The world has changed. Now here's the stranger one. Z squared. Z is a function of x and y, isn't it? If you rearrange it, isn't Z always going to be a function of x and y? So this thing is not 0. This guy is 0, but he is not. This guy is 2z times the partial derivative of z with respect to x. And the number 9 gets you 0. Do you see that it's very similar in a lot of ways to the Calc 1 implicit? Do you notice that there is a partial derivative here, the guy we've been asked to find? Now, don't we still have a little bit of work, but it's very similar work to what we just did. What would be a good move on my next line? What should I do to both sides?
Subtract 2x.
Would you agree that we would then divide both sides by z? and then make it look pretty. Great. Is this function symmetric? Great.
Yes.
Yeah.
Yeah. If you switch the x's and y's around, don't worry about the z's. But if you switch the x's and y's around, don't you basically get the same guy? Which means then, couldn't I get this one for free? Great. Remember what you do, you switch the x's for y's and the y's for x's. Well, here there's only an x, so it gets switched for a y, and they're done. Cool. Yeah. Let's do another guy that you hopefully recognize.
Can you place the just done notes to the left so we can still see it?
There we go.
Thank you.
You recognize who this guy is? In 3D space, what would that look like if you drew it?
An ellipse?
No. 5x squared plus 4y squared plus 5z squared would, but not x, y, and z. In fact, we did a whole section, well, part of a whole section, was devoted to finding this guy. It's called a plane, right? A flat piece of paper, right? Linear combinations of x, y, and z. Now, does it typically look like that? Not necessarily. Couldn't you rearrange that in lots of different ways? You could call it, with a bit of algebra, couldn't I rearrange that to be z equals a function of x and y, for instance? I'm going to leave it in that format. Let's suppose I wanted to find our partial derivative with respect to x. Well, wouldn't this guy get me 3? What would the 4y get me with respect to x?
0?
0, right?
Mr. Robertson,
Hi.
sorry, why we differentiate 3x again, and like 5z, we add dx over dz over dx after 5z. Why is that again? Sorry.
Oh, the question is find dz by dx. So I'm taking this expression, this implicit expression, and I'm differentiating all its parts with respect to x, with the ultimate goal of eventually telling you what the partial derivative of z with respect to x is. So the process involves you taking the original implicit expression and differentiating all its pieces, partial derivatives, with respect to x. So 3x gets you a 3, 4y gets you a 0, and want this guy, well, this guy's kind of weird. 5z. 5, agreed.
This becomes 5 times dz dx.
And you begin to see a theme with this implicit thing. The z's and the z squareds and the sine z's and whatever else they chuck at you. Isn't it going to be basically the derivative in the usual way, finishing with a dz by dx, partial dz by dx? And if you differentiate the number 10, you get 0. In this case, subtracting 3 from both sides, it's a number. No matter what x you have, right, no matter where you slice the shape, the derivative ends up being negative 3/5. What that is kind of showing me is, I don't know if you can see this, don't I? Right, imagine this is a plane, right? That's what it looks like in 3D space. I'll give a little bevel, right? You see it? Now, if you slice this thing, say, parallel to the x-axis, don't you just get a straight line? And I guess I should do it this way. Isn't the straight line going to have a negative slope to it? And that slope is always going to be negative 3/5. Now, if you take this shape, right, but you slice it a different orientation, right? You imagine slicing it parallel to the y-axis. Don't you get a different line slice with a different slope? And that's what dz by dy would look like. So you can imagine that in one orientation, the slices parallel to the x give you a straight line with one slope, and then if you cut it parallel to the y-axis, you get a different slope. So that is not a surprise to me, but it's kind of interesting that it came out. Are we good? So implicit differentiation essentially uses the same modus operandi, right? The same method that the old Calc 1 thing did. We just have to think in terms of z is special. Z is a function of x. Oh, and by the way, isn't z also considered a function of y? So I could go through this process and do a partial derivative with respect to y. Well, wouldn't that be 0? Wouldn't that get me 4? And wouldn't this get me 5 partial derivative of z with respect to y equals 0, and then I could get my second answer. So you can imagine there'd be two numbers, but distinct numbers. They wouldn't be the same as each other. Do you want me to do another implicit, or do you feel that you've got the gist of it and you can have your own practice? Okay, I'm getting kind of nods on that, so I'll use it. So let's move on and upwards. I don't know if you can hear my dog. She's wanting a poo walk, I can tell you that. She'll just have to wait. She is persistent. She is we love her to death. She's old and crabbit. Do you use the word crabbit? Do you know what that means? Crabbit. Do you know old guys who poke you with sticks? We would describe them as crabbit old folk, right? Grumpy, I think that's maybe another word for it. Anyway, if you can find first derivatives, can't you find second derivatives? You would expect that that's a process that is doable, right? So let's look at finding second partial derivatives. And we'll look at the notation for it as well. My wife, I think, is dealing with it. I can hear her voice. Okay, I want to make my life easy, at least to start this process on. So I'm just using a polynomial in x and y. They're nice because they don't involve too much work. Right. Now, notation. I guess I shouldn't need to write that. We know what this guy means, right? First partial derivative. So I would get, with respect to x, I would get 3x squared. What would x squared y to the 4 get me with respect to x?
Two xy to the 4.
Hopefully we all agree with that. Now, we have notation. How do you tell someone that you want a second derivative? Well, in this notation, it's written that way. Now, that's a direct comparison. Can you remember Calc 1, that first derivatives are sometimes written like that, and weren't second derivatives written, well, it's meant to say a y, right? Were written like that. You remember that notation? No? Well, now you do. If you ever see that, it means second partial derivative with respect to x both times. Well, how do you do it? Well, you do it the way you would expect to. Shouldn't you take this guy and find a partial derivative with respect to x? So 3x squared would get me 6x. And this guy here would get me what? 2y to the 4. No surprises, right? Second derivative is kind of intuitive. It is what you thought it should be, right? So far, so good. So I'll put a little bubble around this guy. Make it easier to see him. Let's find its partner. Let's find the second derivative with respect to y. Well, you have to find this guy before you can find the second derivative, right? There's not a shortcut where you can jump right into the second derivative, right? You must find the first and then differentiate that to get the second. So in this case, that gets you nothing. This term here gets you 4x squared y cubed, and this guy at the end gets you 2y. We good? Now, second derivative. With respect to y. If you do this fella, you get what? 12 x squared y squared, and this guy gets you 2. And would you agree, it's not really a surprise once you do enough of these, that these are quite different from each other. I mean, they have x's and y's in them, but they're significantly different, aren't they? Which is what you'd normally expect to see. Nothing strange here. Notation. Do you know this guy here can also be called f little x? So how do they write second derivatives? They call them f little x little x. You see this notation works quite well? Now, what about this fella? F little y, what would this little fella be? F little y, y. Imagine I said to you, oh, let's not do that one yet. Imagine I said to you, do that guy. That would be a fourth partial derivative. And won't you just keep doing x's? In fact, if you keep doing it often enough, won't you eventually get 0 to these polynomials? Eventually they disappear if you do enough derivatives to them, right? Because you keep reducing the power by 1 until there's a constant and then that disappears to 0. And so hopefully right now you're saying, hey, I can do first partial derivatives. If I just use that as my starting point, then don't I just do partial derivatives again? And now I know how to do second or third or 23rd partial derivatives, right? You just repeat the process as many times as you're required. Well, I'm keeping that same function. And I'm going to do something that you might not have predicted was going to happen. I'm going to find that guy, and this is basically just rewriting the earlier one. And then I'm going to do this guy. And I'm writing it in this clunky way for a moment. What do you think you're being asked to do when they ask you to find this guy?
Find the derivative with respect to y after finding
Yes.
the derivative.
Now that might seem to you illogical. Why, if you're calling a variable and the other guy a constant, why are you now changing places and making the guy that used to be a constant the variable and the guy that's a variable a constant? In other words, you're switching the jobs for x and y, aren't you? That is allowed. And it might not seem to be a very useful thing to do, but surprisingly enough, it is very useful to do. It tells you stuff. Now, if you take this guy then, but you differentiate with respect to y, and would you agree that bit there gets you 0? And doesn't this bit here get you 8xy cubed? Now, notation-wise, not very pretty. Now, why is that not very pretty? Well, you read it from right to left. In other words, if somebody said, do this, I would read that as find the partial derivative with respect to x first, and then find the partial derivative with respect to y. That's exactly what I did there, right? Now, do you notice because of this, why that notation came out the way it did? Can you see that that's giving you the delta squared, and you can see the order yx appearing? Well, you might think, hey, what's the big deal? Well, I wish I didn't have to write this down, but I've got a feeling it's probably better. There's the original problem. Now, if I asked you to do this guy, wouldn't you get him? Now, if I asked you to do that guy, do you see the way the notation works is that they don't have the same flow to them? So when you see a question asked in this order, you will do x first and then you will do y second. If you see it in this format, you will do x first and then you will do y second. Now, can you see that that could make a difference, right? If you just say to yourself, I'll do an x, I'll do a y, who cares, you know, it's going to work out. You know, strangely enough, 90% of the time it will be the same answer, but that's something I'll talk about shortly. But you have to make sure that you understand the order in which a derivative has been calculated. So here is an example of a third partial derivative. It's a bit clunky, that notation, but that's it. The 3 tells me it's a third partial derivative, and this here, that looks like a 2, but it's meant to say a delta. Who do I do first? Right, so I'll start with f. Who do I do first? X or y?
Y.
Okay. Which would get me that guy, right? Who would I do second?
Y.
Y again. And then, well, I guess I could have called that dy, but too late now. Then I would do the x. So in other words, 1, 2, 3, right? Suppose you were asked to do fxx, yy, which is a fourth derivative. Right, so you're going to do 4 partial derivatives, one consecutively after the other, using the previous answer, and that's the guy you differentiate to get the next level, and then that guy's your starting point for the next, and so on, 4 times. In this question here, wouldn't you do x first, y, x second, a y third, and a y fourth? Agreed? Now, if I can return back to this example. We just found this fella. And he was equal to 8x y cubed, right? Let's find the other version. Let's do this guy. Let's switch the order, right? See what happens. Right. If you differentiate this fellow with respect to x or y, who do I do first in this notation? Y, agreed. So differentiate this fella with respect to y. You get nothing. Out of here, you get 4x squared y cubed. And out of here, you get 2y, right? Now you differentiate this guy with respect to x, and what do you get? Well, with respect to x, you get 8xy cubed, and doesn't that guy get you a 0? Oh, 90% of the time, the two things end up being the same thing. 90% of the time. But 10% of the time, they are not the same thing. They differ in some way. Sometimes it's minor. Sometimes it's a plus where a minus used to be, or vice versa, right? Sometimes it's a square and a cube that switch places, right? But they are different. And because of that 10% of the time, you have to be really careful that you're doing it in the right order. Because you know what Murphy's rule will say? The one time that you don't bother about doing it in the right order, isn't that going to be the 1 in 10 times where it was important? Right? Because you're going to get into a kind of, and I can understand why, of a lackadaisical thing where, it doesn't matter, I'll do the x and then the y. It's a second derivative. I know it's going to probably be the same. And the last 8 questions, it was the same, so I'm cool. But, you know, question number 9 is going to be the one that's going to bite in the bum. And isn't question number 9 probably the one that ends up being in the final exam? Because that's just Murphy's Law. Right. So, a very interesting guy called Clairaut, at least that's my way of pronouncing him, he came up with an explanation of when does this happen? Because it doesn't happen all the time. For what functions, right? For what original functions is the property that the 2 second derivatives are the same thing, right? So if I do it in a kind of abbreviated form, Clairaut's theorem says that for a specific kind of function, that this is true, right? That both versions of the same answer. And do you know what the connection was? What made this true and what made it not true? If the original function is continuous, right? Now, continuous is, right, nice flowing hills, no funny volcanoes, right? No funny rips in the surface of it, right? Those weird, you know, discontinuities that you might have been looking at in an earlier section, right? If it's just a plain old, every value of x, y works, and the surface just looks like an English, countryside with flowing hills. For those functions, this is true. Which does mean that can't you use the opposite as a test? You can find this guy and you can find this guy. And if they're not equal to each other, isn't that telling you that the original function is not continuous, right? It's got a problem somewhere. Because sometimes, can't you look at a really, really ugly function, and if we didn't have the advantage of software, you might not know if it's got a problem, right? You might not know if it's got a funny volcano hill somewhere, or a rip in it somewhere, or something, you know, some discontinuity. By the way, even the software fails you. Doesn't the software only look at the X, Ys that are in the frame? Couldn't it be a really ugly thing happening away over it? X is 1,000,000, Y is 2,000,000. You know, exaggerating, but couldn't it happen somewhere off screen? So you can't just rely on, I'll plug it into my calculator, my graphing software and just look at the picture, because there is at least a possibility, isn't there, that the bad thing that's happening to the curve happens at some obscure, faraway point that you would never see on their software. So even that's not a guarantee. So Clairaut came up with a really cool trick, for want of a better word, that if you know the function is continuous, that you only need to find one, and then you can tell what the other one is. And it doesn't need to be symmetric, right? You notice this function here is not symmetric, yet this is true. And it doesn't even need to be a nice function. Do you know, it could be the ugliest quotient rule with a chain rule inside a product rule. Right? Can you imagine some, you ain't getting that, right? But can you imagine you got that question? Right? It might take you an hour to do it. But if the function was continuous, can't you just say, well, I know what the other second derivative is because it's continuous, and I don't need to calculate it. So that would be cool. Are we comfortable with this process? That second derivatives are just repeating the process a second time, right? Differentiate and then differentiate again. The change in the game here is that you can switch who is the variable each time you do a derivative. So you could do a third derivative where you did an x first and then a y and then back to an x, for example. Now, Clairaut's not finished. Clairaut also figured out, provided f is continuous, and this isn't precise, but to me continuous just means a nice surface, right? Nothing weird happening, right? None to see here. So if f is continuous, he found out this. Do you know these are fifth derivatives? And can you see the order that you're going to do them? And me personally, I like this notation because I read from left to right, and so I say x, then y, then x, then x, then y, right? In this case, you go x, 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 then finish with two y's. In this one, you start with the two y's, and you finish with three x's. Clairaut discovered that any level of derivative, as long as it consists of the same number of x's and y's, they all end up being the same answer. In other words, order doesn't matter. You can choose to do a partial derivative that is continuous in any order you see fit. Now you might think, why would that be helpful? Here's an example of why it might be helpful. Here is a ugly looking function. At least it's ugly in terms of x. The y's aren't bad, right? And suppose you were being asked to find the following. X, Y, Y. Now, according to the order, shouldn't you do X first, Y second, and Y third? Let's look at that as a puzzle. Do you really want to differentiate that with respect to X? No. So, why don't we change the order? Well, let's see why that order is much less work. Right, I'm starting off with this function. What's its partial derivative with respect to y? Well, what does that horrible mess get you? With respect to y? A big fat 0. Now, that gets you, what, 10y to the 9x. I don't have a problem with that, right? Now, can you differentiate this guy again with respect to y? Yeah. And won't you just get 40y cubed x? Now, can I differentiate that guy with respect to x? Yes. Do you see that that third derivative was almost trivial? It was easy. because I use Claro. Now, we have to make an assumption here. Well, you just assume that every function that you're ever going to do a partial derivative of is continuous. Let's just assume that Claro's picked the questions for us, right? And he's made sure they're all continuous. And if we make that assumption, can you see that choices of order that you do things is kind of cool? So if I have an ugly triple partial derivative, and I look at the original function, don't I have the power to choose which order to do the variables in? And some orders are less work than others, at least in this question, that's true. And so I would choose my order appropriately. It's amazing, people's brains. When I see something as elegant as that relationship, sometimes I think, how did he even think about that, how it was true? I mean, the proof of it is horrendous. I can't even tell you if I remember the proof. If I did, it's long since disappeared from my memory. But it's been proved that provided a function is continuous, any order of derivatives will get you the same result. There's something quite elegant and pretty about that entire process.
Professor Robertson, I had to step away for a minute.
Okay.
Whenever you were calculating out the f double y, shouldn't that have been 90y to the 8th?
Oh, that looked like a 4 in my brain. Fixed. Did you all catch that deliberate mistake as he did?
I was just about to ask that as well.
Do you know what some of you do? I'm making this up because I can't, see in your head. Do some of you just fix my mistakes as I'm doing them? And so you don't even bother telling me about it anymore. It is helpful because not everyone notices that it's a mistake, and then they go back and they look at their notes and they wonder how did that turn into a 40 when it should be a 90? And the answer is almost always because I made a mistake, right?
You also dropped the cubed on the x.
Fressen. We even happier now?
Yes.
If I was self-conscious, this would bother me, but it honestly doesn't. In fact, it actually cheers me up, because what that tells me is that you know what the heck you're doing, and which means my job is done, right? You knew that was a mistake, and you knew what it should have been. And you would only know that if you understood the process, right? If you didn't understand the process, you would just be writing it down and say, okay, I don't know why that's 90 or not 90. I don't even know why it's 40. I'm just writing it down because that's what he's written. But the fact that you can pick it up is a really good sign. So I'm pleased about that.
One question, if I could, about the continuous nature of it.
Yes.
Is this continuous as strictly defined as continuous over the set of all, or the domain of all real numbers, or if say
on its domain, only on its domain.
Okay, so if we get a problem of a restricted domain, for example, then then we can do this assuming that it's continuous over the restricted. But it would come out necessarily differently if the domain were instead all real.
Yeah, if you did all the real, for instance, a very simple example of the problem going awry would be something like this. Would you agree that when x equals y, this function has trouble, right? In fact, maybe I should make it x cubed and y cubed. Would you agree that x equals y, this function is going to be 1 over 0? Right, this guy here. Right, if you sketch that function, there would be a tear along the line y equals x. And it might be a tear that looks like like 2 sheets of paper going upwards. It's like a 3D version of a vertical asymptote. It could be 2 sheets of paper curving downwards, but whatever it is, it's got a problem, right? And if you did the partial derivative xy and then yx of this guy, you would find that there was an issue with what the answer looked like. And that would be Clairaut would saying, yeah, you got a problem with this function, so don't do x, y, and yx. You'd have to do them separately. My gut feeling is that the answer would be different in the sense it'd be a negative in one and a positive in the other, but you'd have to quote me on that. But sometimes the function's fine. Even in that example, isn't the function fine as long as you keep away from x equals y? Would you create, you know, a small subset of this function? The function would be quite continuous and would be safe. So, I think we've reached a perfect finishing point.